I'm David.
And I'm Darwin.
We are two master students at the Institute for Astrophysics of the University of Vienna, and we built a demonstration telescope for the Lange Nacht der Forschung, which was an outreach project in many scientific institutions on the 20th of May 2022. To be precise, we built a model out of Lego to explain ALMA. Yes, you heard that right, Lego. And we would like to explain to you how we built it and how it works, which in turn also explains how ALMA works. ALMA stands for Atacama Large Millimeter Array and is located, as the name suggests, in the Atacama Desert in Chile. ALMA observes radio frequencies, which is light that has a longer wavelength than infrared, and is typically emitted by gas or dust. The array in ALMA hints at the fact that this is not one single telescope, but rather many antennas talking to one another, which in the end leaves us with a picture. This process is called interferometry. Interferometry is used whenever telescopes become too small to make useful pictures for scientists. It uses clever mathematics and precise technology to calculate what something must look like when you get different pictures of an object from different locations. But more about that later. ALMA's antennas can move with the help of lift tractors. This is because the antennas give us different pictures depending on where they stand. Those tractors move them as much as 15 kilometers for very broad constellations, but you will hear all about moving antennas later when we show you the actual model. So, when Professor Hacar asked for help with the project, David and I came to assist with the Lego and the electronics. Little did we know what lay ahead. The Argelander Institute for Astronomy in Bonn were the first to come up with the Lego model and kindly supplied us with the plans and the electronic parts. When we began, it became clear that the electronics was in a very, unassembled state. This meant that the professor, David and I needed to make a plan. Our plan was 1. Understand how the electronics actually work. 2. Experiment with a prototype. 3. Panic! 4. Mass production. The understanding part did not take us too long, and we swiftly started soldering together parts of the prototype. The thing was that everything needed to be soldered together. The connectors to the PC, the connectors to the wires, and the wires to the magnetic sensors. This is, by the way, how the PC knows where a telescope is, through a magnetic sensor in the base plate of each individual telescope and a magnet in the stem of each individual telescope. This magnet then closes a circuit, and the PC just measures which circuits are closed. After the prototype with our own ideas that differed a bit from the original fabrication of the University of Bonn seemed to be working, the next point on our plan was panicking. We had barely 2 weeks left and pretty much none of the electronics was finished. Also, none of the Lego was assembled and the table on which everything would stand was not done. So we can tick off the panic part easily. We then built the Lego with a good part of Professor Hacar's research group. And that was very cool, to be honest. Building Lego at the university with pizza paid by the professor was really something. Anyway, back on track. Now that the Lego was built and the table was in construction, everything came down to David and me finishing the electronics in time. For this, I even brought my own soldering stuff from home. And we were soldering like madmen. On average, we managed to pump out a new completed base plate every 10 minutes. On this path, we had a few headaches. We had to think of a way to wire this monster in a sensible way, and thankfully Darwin came up with one after we wired the first 16 antennas in a very clumsy way. To make you understand how bad all of this was, we called a section of 8 antennas a kraken because it has 8 arms and is terrifying. But in the end, it all worked out. We finished all of the 43 antennas and were even able to make the backboard functional, and all of that in just 2 weeks. Here is me, David, explaining the whole thing on the table.
So here we have the model that we assembled for the purpose of demonstration of interferometry. What we have here is the Lego plate. It is 1 times 1.2 times 1.2 meters, which is 1,000th of the real scale, which is 1.2 kilometers times 1.2 kilometers. We try to approximate the positions of the antennas here. We also have small Lego antennas, just like this one, on the table that are also functional. I will explain later. On the screen over here you can see the ALMA configurations. This is the ALMA points as viewed from above, so the individual positions that are currently occupied can be seen in the left upper panel right here. The thing that ALMA is trying to solve is that you can't build huge telescopes to make good pictures. There is a certain limit to how tall or how big in general you can build a telescope. There's a technical but also financial So what you do instead is you build an array, which also comes into the name of the ALMA, of the Atacama Large Millimeter Array, of moderately sized telescopes. In those you can then later, by a lot of clever mathematics and techniques, think about the picture or reconstruct the picture that you are actually making with those telescopes. One thing I should add before we continue with the demonstration is that those telescopes or some antennas don't make traditional pictures in the sense that your phone makes, for example. They just measure the flux of light coming from a certain position. And with, again, mathematics, they calculate what could cause those fluxes of light at the different positions, and from that they make a picture. On the screen we try to visualize that. This is the ALMA from above, so again which positions are occupied. This is the ALMA from the perspective of the source. And this is the source that we want to observe. In this case it's a galaxy. And this down here is the Fourier transform of the source. This is kind of how the telescope sees it. And here we have the coverage on the Fourier plane, which is basically how much of this ideal Fourier transformed source the telescope can see. And you can see out of these two, the telescope builds the Fourier transformed picture of the source, which is then back calculated with, again, mathematic to the source, to the picture of the source that we can actually see relates to reality. Okay, so now we'll try to explain the positions and what they mean. You can see that currently those are all very compact, so they're all in more or less small circuit, which you can see here. It doesn't give us a lot of detail, but structures are very, very visible, so to say. I can easily determine how this is how tall kind of the galaxies on our visual plane, and this is how broad and stuff like that. I can determine rather easily. If I now start moving the telescope outwards, again, this was one of the main goals of our project, that the telescopes can just be picked up and put somewhere else. If you do that, I'm now, as you can see, moving them further outwards. Those are telescopes that are currently not in use. The real ALMA, they don't just lay on the ground, just for information. If I do that and the program doesn't crash, you can now see that the image has changed broadly. It is now that the configuration is much farther apart from each other. It has a longer baseline, and you can see in all pictures that it changed, especially in this one. The individual structure, I'm now not as easily convinced that the galaxy is this tall. It could be this tall or that tall, I'm not entirely sure, but you can see that the individual arms and the finer structures are way better. The best solution, of course, would be to just add more telescopes. This is, of course, a financial problem, but also technical and computational challenge that must be overcome. However, if you do that, you get a nice compromise between the two, getting the basic structure right, as well as the fine detail.